Good morning. Initially, I would like to thank all the organizers of the SCGI Symposium for the invitation, for the opportunity. It's a great pleasure for me to be here. It's my second time in Arequipa, and it's very nice to be back. Before mentioning some applications, challenges, research opportunities that we are investigating in Brazil, I will start giving you some information about our institute, our university. I am a professor in the Institute of Computing. This is an aerial photo of the university. Officially, the university was founded in October 5th, 1966, which means that it's a young university, even in the Brazilian context. Unicamp is a public university. It's located in the city of Campinas, the state of São Paulo in Brazil. We have 24 units. 24 units, 10 institutes, and 14 schools. For instance, we have Institute of Mathematics, Institute of Physics, but we also have School of Engineering, Medical School, etc. So these units are related to teaching, research in different areas of knowledge. We also have a very large hospital. It's located inside, within the campus in Campinas. We have 21 interdisciplinary research centers, 2 technical high schools, and several support units. And the universe of people in our university is about 50,000 people. It's a very large university. We have 66 undergraduate courses, 153 graduate courses, including master's and PhD degrees. We have approximately 41,000 students, 3,000 in high school, 18,000 undergraduate students, and approximately 20,000 graduate students. So we have more graduate students than undergraduate students. This is a very interesting fact. We have about 8,000 staff members, 1,900, almost 2,000 faculty members. They work full-time in the university. Actually, 90% of the faculty members work full-time in the university, and 90% of the faculty members have PhD degrees. So this is in the entire university. Unicamp concentrates about 15% of the total scientific production in Brazil, and it's responsible for 12 of the undergrad students in the country. And the same percentage of theses and dissertations. According to the Times Higher Education in this last period, 2016 and 2017, Unicamp is in the first best position in Latin America. It has among 50 best universities in the world under 50 years old. It's in the 12th position on the list of BRICS universities. So this is an international ranking, and we are in the top position in Brazil in terms of patents and licensing patents. Well, in the institute, we have 2 undergraduate degrees, a Bachelor of Computer Science and a Bachelor of Computer Engineering. We start our undergraduate course in 1969, and it served as a model for several other courses in Brazil. Our graduate program started in 1977. We have awarded more than 800 master's degree and almost 200 PhD degrees. Many students have received the awards for best theses and dissertations. We have the highest rate, it's the number 7, in the evaluation of coordination for the improvement of higher education personnel. It's a public foundation that evaluates our graduate programs. In general, our graduate and undergraduate students participated in several competitions and contexts. For instance, ACM programming context, the Brazilian program Olympics, Imaging Cup, hackathons, Google Summer of Code, Brazilian robotics competition, etc. So there are many activities where the students, graduate and undergraduate students, can be more involved in this kind of activities. Well, now I will briefly mention some research projects, some objectives, some motivation for these projects, some open challenges, some applications, and also some trends. Well, as we know, images and videos convey valuable information. And the essence of image and video data can be extracted from visual patterns. So on the bottom of the slides, we can see several different images, and they are related to a certain knowledge domain. For instance, medicine, remote sensing, biometrics, agriculture, biology, or microscopy, etc. So there are many areas that you make use of images and videos in our daily life. Some common objectives in image and video analysis are, well, extraction, analysis, and understanding of useful information from a single image or a sequence of images. We usually intend to search for automation of tasks that the human vision system can do. We try to emulate what a person can do and transfer that knowledge to a machine. Another important objective is the development of theoretical and algorithm bases to achieve visual understanding. In general, this is performed automatically or semi-automatically. Some challenges associated with this problem. First, the input space is typically high-dimensional. So one difficult thing when we explore some applications in imaging, video analysis, is the input space is in a very high dimensional scenario. So the computational cost is usually very high. Nowadays, we have a diversity of sensors for vision, audio, light, temperature, direction, acceleration, etc. Another open challenge is how to map efficiently from images, videos to flexible and scalable models. This is usually a hard problem. We don't know yet how the brain processes visual stimuli in humans. So we need to evolve on that to better comprehend how we can solve some difficult problems, especially when you use vision-related tasks. How to generalize from few examples to large data sets. This is another difficult problem. And memory and processing are finite computational resources, so we need to be very efficient when you develop some algorithm. Another difficulty in this field is Computer vision, machine learning, image processing are interdisciplinary and multidisciplinary fields, which means that we need to know several other disciplines in order to contribute in a more effective way. So we need to know a little bit about psychophysics, cognitive neuroscience, neuroanatomy, computer vision, machine learning, signal processing, computer science, information theory, geometry, statistics, visualization, among others. So it's a very complex scenario. Despite these challenges, continuous advances in digital technology and the development of new and efficient algorithms have allowed an increasing number of applications. I have already mentioned some of them, but we can apply our knowledge, for example, in medicine, microscopy, biology, agriculture, remote sensing, industrial automation, astronomy, military, security and surveillance, forestry, science, etc., artists, etc. Now I will briefly mention about some projects that we are involved in UNICAMP. Since some pre-processing activities to more complex and more complex and difficult tasks, for instance, object detection, object classification, etc. So I will start with image threshold improved by optimization methods. So typically we start with original image, and sometimes this image is not in a better or in a convenient quality level. For instance, the first image was acquired in a non-uniform lighting condition, so it has poor contrast. In order to improve the quality of this image, we can, for instance, apply some bio-inspired algorithms such as genetic algorithm, particle swarm optimization, simulated annealing, pattern search, etc. So I think it's a common sense that if you have a better input image, you have a great chance to produce better results. So although this is a step, a pre-processing step, it's very important to improve the quality of the original image. And the second image, for instance, was obtained by a classical thresholding method called OTSU. So we can see that the result is very poor for this kind of technique. Whereas in the other techniques, we can see several details that were not possible in the original imaging. This is another example of the same approach. Here we are maximizing the SSIM metric, is the structural similarity index metric. So we have an objective function. We need to maximize that metric. This is another topic, image approximation based on triangular meshes. Before my presentation this morning, we watched some of the works performed here in UCSP. So this is related problem. The idea here is to create an alternative structure different from matrices for representing images. Why we do that? Triangular meshes are usually more compact. We can use triangular meshes as a compression method. They are more flexible. They are adaptive to the image. So there are several advantages when you use, for instance, a triangular mesh instead of a matrix to represent an image. In these cases, we are using only 0.1% of the original number of points instead of all of them. Here we have a terrain represented by non-overlapping triangles in order to create this surface. So after that, we interpolate each triangle by using a linear, a quadratic, or a cubic surface. So we can have a flat surface, or we can have a smoother surface. Here's some other data structures. All of them use triangles. So regular triangular mesh, a quad tree, Delaunay regular triangulation, data-dependent irregular triangulation, and irregular based on features. Each one has advantages and disadvantages. Here, an interesting application. So instead of using the original image, we are using the triangular meshes to discover how the number of observers in order to have full coverage. So in order to have this concept of visibility, 2 points must be connected to a straight line with no occlusion in between them. So in that case, only 41 observers are sufficient to cover the entire image. Only those black regions do not have coverage. So it's an interesting problem. It's an optimization problem in order to, for instance, position some observers, some towers, observation towers, etc. Well, another project is how to reconstruct 3D object from counter data. So in this case, we have slices generated from, for instance, CT or radiographies, images. And the idea is to connect two adjacent slices in order to produce an external surface. We have to do that by connecting two adjacent contours. And after that, we create a triangular mesh between each consecutive slices. After that, we have the reconstruction of the entire object. Here we have some examples. On the left, we have the triangle mesh itself. So we can see some small triangles representing the external surface. On the right, we have a real object. So we can see that they are very similar. I didn't mention in the beginning of the presentation, but on the bottom of the slides, I'm including some related and recent publications that we had in every topic, okay? On the second, on the right, we have, for instance, the humerus bone, and we have an ampliation, a zoom for the bottom and the top regions. Some other complex structures, as we can see, the objects can have holes or curvature, very complex curvature areas. And on the bottom, we have the objects after a biofabrication process. So it's similar to a 3D printer. So we submit each file to a machine, a biofabrication machine, in order to produce an object in real dimensions. Another research topic is adaptive human skin segmentation. Segmentation of human skin is very important because we can think of as a pre-processing problem. So if you want to recognize or detect a face in an image, we can start, for instance, by detecting skin, human skin in an image. If you have human skin, we probably have a face, a human face in the image. So some applications related to adaptive human skin segmentation, face detection, gesture analysis, content-based image retrieval, nudity detection, most for adult content filtering purpose. We can think of skin detection as a classification problem. Actually, it's a binary classification problem. And our purpose is to determine which pixels belong to skin or non-skin classes. There are several challenges in this problem. For instance, variation in scene illumination interferes with the appearance of the skin. So if you have different illumination conditions, the color of the skin may vary. Different cameras may produce distinct colors, and ethnic diversity promotes various skin tones. Então, this makes the problem more challenging. This is an example of the result by using one of our methods. Actually, we have investigating this problem. As we can see in the bottom of the slides, there are so many other strategies for segmenting human skin. In this case, we are combining general and local probability maps. This is another research topic, the identification of computer-generated images versus digital photographs. The idea here is to differentiating computer-generated images from real photographies. In this kind of problem, forensic techniques can play a very important role. For this problem, we collected about 10,000 images, 4,800 synthetic images and 48 photographies with large diversity of image content and quality. We implemented 13 methods and compared them using the same validation environment with a common benchmark protocol. From the results, we conclude that we can achieve up to an accuracy rate of about 97% if we use some sophisticated fusion schemes, which represents a reduction of 57% of the classification error if you used the individual approaches. This is an example of the data set we used. As we can see here, the degree of realism is very high. Sometimes we think that an image is synthesized, but it's a photography and vice versa. So the idea here is to use some descriptors such as edges, blurring, effects, focus, etc., in order to identify real and fake images. Another important problem is the text identification in images and videos. So as you can see here, the texts can be positioned into several locations. We can have different languages. They can be placed in a curved surface. They can be in horizontal or vertical position. The surface can have a discontinuity. So the idea here is to identify the texts and basically put in a bounding box enclosing the detected texts. For this problem, we have used a representation called visual rhythm. The visual rhythm is a very interesting representation. It's defined as the union of certain slices. And these slices are extracted from each frame of a video. So, for instance, in that picture, we are extracting just one column from each video frame. And after that, we combine all of them. So we are mapping a video to an image. Instead of using a column, we could use a row, a diagonal, multiple lines, multiple diagonals, multiple rows, etc. So this illustrates how the visual rhythm is constructed. This is an example of a visual rhythm. So we constructed from 872 frames, and now we have just one image. For the video caption detection, we are interested in detecting these portions of text in any position in the frame of the videos. So as you can see here, the positions of the captions are remarkably visible in the image. Okay. Some other examples of the use of visual rhythms in order to detect caption. This is an overview of the method. We start with video in RGB format. We extracted some lines, in this case, a zigzag curve. This will generate the visual rhythm. After that, we apply a segmentation process. It's basically the detection of those rectangles in the image. And after that, we can classify the regions. We defined some rules in order to consider a text as a caption. For instance, the lowest line of the caption should be at least 1/12 of the screen height, just above the bottom of the screen. So this is a simple rule. The minimum duration of a single word subtitle should be 3/2 seconds. And in order for a spectator to clearly perceive a caption transition, at least a quarter of a second needs to be inserted between two consecutive subtitles. This is an example of a visual rhythm generated by zigzag curves. So we can think of a multi-scale representation if you use more curves. We can also use some other and complex curves, for instance, the Hilbert curve, in order to generate the visual rhythm. Well, another important topic in computer vision nowadays is the detection of anomalous or abnormal events in videos. There are several applications on that. One interesting fact is the United Kingdom, although has just 1% of the world's population, concentrates 20% of the world's closed-circuit television cameras in the world. So there is a large, great investment in surveillance in some countries, in particular England, in the United Kingdom. According to metropolitan policy, although they have this large amount of cameras, approximately only one crime is solved for every 1,000 CCTV cameras per year. So this is an example of an observation room. So it's a very exhaustive task. Most of the surveillance systems nowadays are based on the observation by human operators. So they are dependent on the capacity of the observers. So they can make they may fail, they can be tired, etc., and make some mistakes. So ideally, we'd like to have not a passive surveillance system, but a more active surveillance system. The system, for instance, could warn the user when an abnormal situation occurs. With the availability of cameras in several environments, for instance, airports, train and bus stations, shopping centers, stadiums, hospitals, schools, buildings, roads, etc., this kind of system have received much attention. For this problem, we also use the visual rhythm constructed in a similar way as the previous problem. So we extract some patterns from the visual rhythm. So in the first column, we have the video, and on the second line, we have different visual rhythms generated by different videos. Now the idea is to extract some particular patterns from each video or from a set of frames in order to differentiate, for instance, a violent action or an abnormal action. This is an example of a video sequence. This happened in Sweden. A person fell off the platform, a train platform, and another one, instead of helping the person, actually stole the person's wallet and run away. And the situation gets worse when the train arrives in the station and run over the person. After this kind of situation, there was a great initiative in Sweden in order to create more active surveillance cameras. The person didn't die, but he lost his left foot. So this kind of anomalous event could be, for instance, detected by an automatic system. Another examples of data sets used in experiments in order to validate the ideas. There are some simple data sets, more challenging data sets. Another scenario is in a subway data set where some people are walking and in the opposite way. Sometimes they do not pay for tickets, etc. So they should be recognized, for instance, in a surveillance system. Also in this context, recognition of human actions or activities, depending on the case, have received much attention from the community. It's a challenging task. The idea is to automatically identify actions or activities performed in a scene by one or more agents. There are several applications related to this topic: surveillance, health monitoring, user interface, sport video analysis, smart home monitoring, vandalism prevention, accident monitoring, etc. On the bottom, there are some publications related to this topic. This is one of our interests in Universidade of Campinas. Here, examples of some data sets available in the literature. For example, violence in some sports, violence in the streets. Here's some simple data sets. For instance, Wiseman KT8 data set. In this case, the background is static. They are not moving. The background is not moving. Another data set, the Mojave data set. These data sets are used to learn some situations and improve our methods. There are many data sets available in the literature now. There are some indoor scenes, outdoor scenes, daily living situations, etc. Situations in films, documentaries, parking lots, etc. Another interesting problem is the prediction of action, human actions. So instead of recognizing the action after it was performed, the idea is to predict an action or activity before it happens. So it's a more complicated problem, but of course, very interesting. So from a subset of frames, we want to identify what a person will perform in the future. Here an example of another special case of action recognition called first-person action recognition. It's a more recent problem in computer vision, and the idea is to put the camera, in general small cameras, in the observer. So these wearable cameras can be attached, for instance, onto bike helmets, belts, animal halters, etc. Some applications for this kind of situations are sports, security, healthcare, visual, life logging. So after several hours, for instance, of capturing some videos, we can analyze and extract some patterns. In this problem, you also employed the visual rhythm to find some texture and shape descriptors. In this case, we use 7 different information: the grayscale images themselves, the intensity gradients, X and Y direction, it's more related to shape, the optical flow for motion feature, and also the gradient of optical flow images. We have tested our method on 2 different data sets: the dog-centric activity and JPL first-person interaction data set. So in this case, we extract those 7 types of information and create the visual rhythm, and the classifier will consider the patterns extracted from the visual rhythm. We are always changing a video sequence into an image. Another interesting problem is the classification of emotions through facial expression analysis. So this kind of problem has several applications in image retrieval, human-computer interaction, action recognition, etc. And the idea is to identify different emotions demonstrated through facial expressions. So some examples of data sets available in the literature. This is the JEF, it's a data set constructed in Japan. It has a small number of images containing 7 facial expressions, and the idea is to differentiate from one expression to another one. In this data set, we have, for instance, happiness, sadness, surprise, anger, disgust, fear. These are the basic emotions in the data set. Another data set is the AR face. And as we can see here, there are some difficulties in order to recognize a certain emotion. The person may be wearing a scarf, an eyeglass, sunglasses, etc. So we have lighting conditions, we have occlusions, so the problem becomes more difficult. Another data set for this problem. Another one called CANADE. Related to emotion classification, we have age identification, gender identification, and ethnicity identification. So an interesting problem is to detect the age or of the gender of a certain person in a video sequence. And most of the times we have to extend these 2D ideas to 3D data sets in video sequences by using temporal, spatial and spatial temporal features. Another important problem in video analysis and computer vision is video summarization. The idea here is to create a short version of a certain video, preserving as much relevant information as possible. So instead of watching, for instance, a 2-hour video, I would like to watch just 1 minute or 2 minute video. This is a very difficult task because in general, what is important, what is relevant to a person is not relevant to a different person. So there is a subjective sense in here. I'll show some examples. Some of them were achieved by using our methods. So the idea is to extract the essence, the most representative frames from a video sequence. Some data sets have annotated, labeled information, so we can compare our results with a labeled data set. In that case, 5 different users selected what they consider the most relevant frames in the video. Another example of this problem, there is a project called Open Video, and there are several different samples of videos for this problem. Another problem that we have been investigating in our group is video stabilization. The idea here is to remove some undesired motion or instabilities or vibrations. It happens when, for instance, an amateur, a non-professional person is handling a camera. So as you can see on the left, we have of course, the original image, the original video, the unstable video, and the idea is to process the video by detecting some important features, for instance, edges, corners, etc., as fast as possible, and stabilize the video. Another example of video stabilization. We can see some differences on the left and on the right. Some details are lost in the stabilized version of the video. On the second image, on the right, we can see some black pixels on the boundary of the video frames. It happens because there is a geometric transformation trying to stabilize the videos For instance, rotation, translation, warping, linear or non-linear transformations. This is a more detailed step of the process. We have to detect key points for each consecutive frames. In general, this kind of problem is evaluated by PSNR, the peak signal noise ratio, or a certain error, for example, RMSE error, which means square error. But there are several situations when this kind of metric does not work. In this case, the ITF, or the interframe transformation fidelity, is the accumulation of the PSNR. So for each pair of consecutive frames, we calculate the PSNR, and then we sum up everything. Here an example of visual rhythms extracted from stabilized and non-stabilized videos. I think it's very clear that the visual rhythms on the left were extracted from the original non-stable videos. And on the right, we have the visual rhythms extracted from the stabilized videos. So now we are proposing some subjective metrics to evaluate video stabilization, since there are several situations when ITF, PSNR, an error metric does not work very well. Another example of visual rhythms extracted from other video, and you can see that in the stabilized version of the videos, we have smooth curves, we have some a very clear disposition of the videos. In this case, the visual rhythm was generated by computing the arithmetic mean for each line of the video, and we shrink all of them into a single column. It's a more, it's a different process. In terms of trends in image analysis, image and video analysis, spatial temporal features are very important. We need to capture not only spatial features, but also temporal features. Optical flow, the histogram of optical flow, etc., are examples of temporal features. The visual rhythm is another example of a spatial temporal feature. Another important approach in this kind of area is the use of multi-scale representation, multi-resolution. We can have better results if you analyze images and videos in different resolution levels. Contextual information, although it's very difficult to identify the context where a scene was captured, but certainly contextual information is very important. For instance, a person running during a marathon it's a normal action. But if the person is running inside a bank, for instance, this could be an anomalous situation. Well, the number of applications for mobile devices, smartphones, tablets, of course, are receiving more and more attention. The use of deep learning, I can say that more than half of the students I'm supervising now are using deep learning for action recognition, emotion identification, even for the pre-processing steps, not only for classification steps. So this, of course, is very important nowadays. Well, deep learning won't solve everything. There are some limitations for deep learning. For instance, the dependency on large number of training samples. We are also dependent on very expensive hardware. So these are some drawbacks. We need faster and more accurate acquisition hardware, for instance, GPUs, VPUs, the use of mobile devices. We need to know how to integrate wearable sensors into our classification process, ambient sensors, camera suites, light sensors, etc. So these are some trends in image and video analysis. Well, this is what I'd like to present today. I will be open for questions. I would like to thank all the organizers of the SCGI symposium again, especially Professor Alex, Professor George, Professor Eric, and the other colleagues. Thank you very much for your attention.
Good morning. You talked in the last slide about the GPUs with the images, and I have one question about the NPU, the neural network processor unit, and if you are working with that. No, the NPU, the neural networks processor unit, and if it's related with the process images in your work.
Some negative impressions in using the neural networks. Is this the question?
Yeah, if you are using the neural networks processors.
Sure, yeah. We have used CNN, LSTM, recurrent neural networks in several problems. So deep learning approaches to identifying patterns in image and videos. I think this is nowadays very important, despite there are some other some problems in this kind of approach. As I said before, for instance, the dependence on large data sets for training, the use of very expensive hardware, for instance, a cluster of GPUs. What else? VPUs. It's very difficult to obtain real time when we are with this kind of approach, unless we have a trained model with so many images. Unless this situation, you have to wait for a long time to have a result. So this is, I think, is the drawback of the deep learning approach. We are trying to balance between deep learning approach and handcrafted features. Visual routing is one of these handcrafted features, and they can produce some interesting results. I think we can have some interesting insights when we are planning, designing these kind of features and see how they work on different scenarios. Most people use deep learning, but as a black box. So we are not interested in using deep learning as a black box.
Thank you.
Hi, Helio. Is deep learning the technique to solve the most of problem in computer vision?
Yes, as I mentioned before, well, we have been using deep learning approaches to identify, for example, if you not only in classification tasks, but in the beginning of the process. Now we can design, for instance, a peer-to-peer deep learning architecture in order to, for instance, reduce the amount of noise in an input image. We can segment medical images by using, for instance, CNN, convolutional neural networks. So most of these problems have been explored with deep learning techniques.
Thank you.
Some other question?
So thanks for the beautiful talk. You're showing some of your interesting work in terms of emotion detection and characterization, and you briefly talked about some of the studies that you were doing identifying gender and age in those sequences. Can you give us a sense of what you actually found out in terms of the differences between genders in terms of how the emotions were characterized as well as age? And does it make sense with the biological literature that we know?
Okay. For gender identification, we investigated some characteristics in anthropomorphic characteristics. So male and female have different distance between, for example, eyes, the distance between eyes and nose, mouth, etc. So first of all, we projected map by using these different distance from facial features. So, well, it's not perfect, but male and females have different distance in terms of facial features. No. Yes, yes. For age, the same thing. Yes. Well, my research field is related to image and video analysis. So, human faces will be the input data for me in general, audio or videos.
So for a given individual over time, you're saying that
We, yes. Yes. Different, yes.
Hi, Helio. I want to thank you also because it was an amazing number of different projects that you are presenting today. So I think that is going to be really fantastic for the students here that are interested in those topics. And now I think they have a more wide vision about the different problems that they can work on. So my question goes also in the topic of deep learning, but basically in the trend. So I want to know, how did you feel that impact of deep learning on your work? When that thing happened, and how do you see that on the future?
Well, in my opinion, we need to know how the neural networks work, but not superficially, in a very detailed level of details. We can use, for instance, data visualization techniques in order to understand how the neurons are connected in a layer, or how the layers are interconnected in order to produce our results. So I believe visualization techniques can help us understand how they work. And I think there is a lot of room for contributions in this kind of area. Nowadays, we have very powerful, companies, Google, Facebook, Amazon, and each one of these companies has its own deep learning framework. For instance, MXNet by Amazon, Café. Café is, I think, Café was developed in Berkeley by a PhD student. But we also have TensorFlow, Keras, PyTorch, etc. So we are more dependent on these powerful companies nowadays. So if you have powerful hardware, you can have maybe conditions to use deep learning techniques. Otherwise, it's very hard. And we need to contribute, in my opinion, in the methodology, how to project very efficient architecture, not a general architecture, but a specific architecture for that kind of problem. And this is not easy. What kind of kernel you use in some filters, how many layers, how many neurons in each layer. So people in general use this kind of concepts in a very blind way, without understanding the profound idea.
Any other question? Hi. I have a question. Actually, I'm working in 3D reconstruction. In the process of reconstruction, there is a part when you have to find the feature points, and later you have to make the match between the points. But I find out that it's not perfect at all. There is a lot of mismatches, or maybe the matches are that don't have the best fit. So I would like to know how can I apply deep learning in my research, and which techniques can I use for this?
This is very difficult to answer. There is no recipe for that. We need to, initially we need to understand the input data, what you have there.
Okay.
After that, well, we have to experiment a lot of different things.
Sorry, in my case, I use a lot of images, a collection of images from different sources. In this case, the images are non-calibrated, so I have to auto-calibrate the images, find the intrinsic and extrinsic parameters, and define infer the 3D points, which I would like to do. So I would like to know how can I apply deep learning, which technique of deep learning can I use to have a better performance.
This is tough one.
Okay, thank you.
Well, I have to know more details about the problem, and maybe later on. I'll be here until Friday, and I'm open for talks, for collaboration, for informal discussions, no problem.